Welcome to Calculus. Today we will investigate optimization questions. We'll take a look at 3 examples. We'll start off with this first scenario where a rancher wants to construct 2 identical rectangular corrals using just 200 feet of fencing. It says the rancher decides to build them adjacent to each other, so they're going to be right next to each other. In fact, they share fencing on one side, right down the middle. Our task is to find what dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area. So we'll start off just by drawing the scenario. It's a word problem, so a good first step with any word problem is to draw a diagram. So here's just a rough sketch of 2 rectangular corrals that have a middle fence in common. Now, for us, once we get that drawn, we need to label the diagram with variables, and really we want to keep it to one variable if possible, as since that'll help us when we go to set up an equation. So I see that these 3 vertical, at least the way that this diagram's presented, these vertical pieces are all the same length. So I'm going to just choose to call those each X. Now, for the upper part and the lower part of the corral, the 2 horizontal pieces, I really need to define those in terms of X as well. So what I'm looking at is the total number of feet of fencing for all the sides, including that middle piece, is 200 feet. So for me to define this upper piece, it's really 200, and then I'm going to subtract from it these 3 pieces that are marked X. So I'm going to say that's minus 3X. But then I need to split that length between the upper horizontal and the lower one. So I'm going to call it 200 minus 3X divided by 2. Now, once I have that labeled, I'm looking really here now for the largest possible area. So the function I want to create is going to be an area function. So area of a full rectangle is going to just simply be length times width. So that's going to be my 200 minus 3x over 2 times x. Again, this is the length and this is the width. So once I have that set up, I can simplify the function so that I could divide by 2 here. This is going to be, and distribute the x. So it's going to be 100, 200 divided by 2 is 100x, minus 3 over 2x squared. So if I wanted to write it in standard form, negative 3 halves x squared plus 100x. And that's my area function. Now that I'm going to use right now in order to find this dimensions of the corral to enclose the largest possible area. And it's the idea of optimization. What I want to do is I want to find the maximum value of this function. If I find the maximum value, that's going to guarantee that I found the dimensions that will give me the maximum area. So to do that, I need to take the derivative. I'm really looking for the local extreme, the local maximum. So I'm going to take the derivative of the area function I just wrote. So that's going to be negative 3 halves times 2. So negative 3x plus 100. And like we do when we're looking for relative extrema, I take the derivative, set it equal to 0, and solve. So with a linear equation like this, solution's pretty straightforward. Subtract 100 both sides, we get negative 3x equals negative 100. And then to finalize that solution, I would divide by negative 3 and get x equals 100 over 3. If I were to write that as a decimal, 33.3 feet. So if I plug that in, that is going to actually be the height here. So each of these 3 walls is going to be 33 36.3 repeating feet, which means if I plug this x value into this expression, 200 minus 3x, 3 times 33 point repeating 3 is 100. So 200 minus 100 is 100, divided by 2 is 50. But then there's 2 corrals, so each of these has a length of 25 feet. And that completes this question. So again, the real task here is to set up an equation, take the derivative, set it equal to 0, and solve. Let's take a look at a mathematical problem. So the previous one was a real life example of a rancher enclosing some property in order to make 2 corrals. Here we're looking at the function y equals square root of x, and we're asking what point on that graph is closest to the point 5, 0. We'll start again by just drawing the situation. This one is mathematical in nature, so I'm going to put the coordinate plane, and let me place this square root function. So that's the function y equals square root of x. I'm also going to place this point 5, 0. So 1, 2, 3, 4, and 5. And what we're asking is, what is the point that's the least distance from 5, 0 on this curve? So it's some point along that curve, and we're really asking which one is closest to the point 5, 0 there on the x-axis. So the idea is we're really looking for a distance, some distance, and I want to find the point that is presenting the shortest distance between 5, 0 and the green curve. So on the green curve, I'll note whatever the point is where that is, that's going to be x1, y1. But for us, because this is a function, we can define y1 in terms of what y equals here. Y equals square root of x. So the way I'm going to set this up is not with y1, but with that specific square root of x. And we'll just go ahead and call this x comma square root of x. Now that will correspond for us because we're about to set up an equation x1, y1. Our point here, 5, 0, is going to be x2, y2. So when I set up my equation, it's going to be the distance. Let's put the general form of the distance formula just to remember it. It's x2 minus x1 squared plus y2 minus y1 squared. So all we have to do is plug in what we've got here in blue and red. So our distance is going to be the square root. We've already labeled them, so it's going to be 5 minus x. That's x2 minus x1, 5 minus x squared, plus, and I should have labeled this y2, 0 minus square root of x squared. So that's a setup. At this point, we just need to simplify that. That's the square root of 25 minus 10x plus x squared plus negative square root of x squared is going to be just x. And so our function here for the distance is going to be the square root. If I flip things around standard form, x squared, combine like terms, negative 10 plus 1x is minus 9x plus 25. So again, that's our function that would represent the distance between the point 5, 0 and the curve. What we need to do is find the closest one. So again, I need to find the derivative of the function and set equal to 0 and solve. So I'm going to find derivative of this. What I'm going to call this is actually a rational power function. Instead of a square root, I'm going to call it x squared minus 9x plus 25 to the power of half. So that helps me take derivative. Derivative here is going to be half times unchanged x squared minus 9x plus 25. And then half minus 1 is negative half. And then I need to use the chain rule to take the derivative of the interior. So that's going to be times 2x minus 9. So then if I clean that up and simplify, in my numerator, I'll have 2x minus 9. In denominator, I'm going to have 2 times parentheses x squared minus 9x plus 25 to the power of positive half. Now, if I set that equal to 0, that's a rational function. And remember, with rational functions, my zeros are going to come from the numerator. So the denominator would tell me what type of x value is undefined for the function, which is informative, but I don't need that information right now. I just need to find out, where does this cross the x-axis? So 2x minus 9 equals 0. I'm going to make a separate associated equation, solve that. So add 9 to both sides. We get 2x equals 9. And then by dividing by 2, we see that we have an x value of 9 over 2, or 4.5. So we are looking for a point. That's the x value of this point here. So we just need to locate what's the y value. So the closest point, if I were to find both the x and the y coordinate, is going to be 9 over 2 for the x, which we just calculated, and then square root of 9 over 2. And I can simplify this. This is going to be 3 over square root of 2. And then to rationalize, I would multiply by square root of 2. So kind of the final presentation form would be 3 square root of 2 over 2. And that's how I want to present this point. 9 over 2, 3 times the square root of 2 over 2. And that's the closest point on that green curve to the point 50. So we've looked at one example that was about area, one example that is about distance on the coordinate plane. Let's finalize with a third example here that involves some right triangles. So here I've got 2 vertical poles. One is 5 feet high, the other is 10 feet high. So I'm going to draw those. There's the 10-foot one. And here's the 5-foot one. And we're told that they're 36 feet apart. So that whole distance is 36 feet. A worker wants to support both poles by running rope from the ground to the top of each post. It's a good idea. It would work as a kind of a anchor. If the worker wants to stake both ropes in the ground at the same point, where should the stake be placed to use the least amount of rope? So we're going to have to locate where this pair of ropes need to be tied here in between the 2 poles to say which point would give me the least amount of rope. So if we were to just pick one, not knowing exactly where it's located, really we're saying we got these 2 ropes. One is attaching to the 10-foot pole, one to the 5-foot pole, and they together attach somewhere in between. Now, I need to calculate the length of both of these red ones together. And so the idea there is I want to find their sum. So I'm going to start off by treating these as 2 separate triangles. And in fact, we could specify these are right triangles. And so really what I've got is 2 versions of Pythagorean theorem. Now they are related because their horizontal legs here are together forming 36 feet. So in order to kind of set this up, I do need to mark here this length of the first left-hand right triangle. We'll just call that x. And then this second one, since together these 2 have to add up to 36, that's going to be 36 minus x. Now, what that allows me to do is use Pythagorean theorem to come up with these two lengths of the hypotenuse. So that's going to be C1, we'll call this C2, and let's set up our two equations. So essentially what we're trying to say is that the distance, this is also a distance equation, is generally going to be C1 plus C2. Now we need to fill in those C1, C2 with expressions from the quadratic formula. So if I was to set up an equation for this left triangle, it would be something like 10 squared plus x squared equals C1 squared. And again, I don't want C1 squared, I want square root of that. And so we'll see for our C1 that equals the square root of 100 plus x squared. We can go ahead and place that. We're going to do something similar for C2. So for C2, what we'd have is 5 squared. That's that upright leg, the pole, plus parentheses 36 minus x squared. We'll go ahead and multiply that out, but that equals C2 squared. So again, I want to take square root immediately. So C2 equals the square root of 25 plus, and so here we should multiply out what's 36 times 36. So that's going to give us 1,296. And we're going to add to that the 25. So that's 1321. So we'll catch up to our calculation. So I'll just put 1296 for now, minus 72x plus x squared. And then if I combine stuff and write this in standard form, it's going to be square root of x squared minus 72x plus 1,321. And that's my C2. Now, I've got the formula then, or the equation written to represent these two rope lengths added together in terms of the triangles that they create with these two poles, the 10-foot and the 5-foot. At this point, I again need to find the amount of rope that would be the least to accomplish this task. So it's an optimization question, so I do need to take the derivative and set it equal to 0 and solve. So I'm going to take derivative of these square roots separately, and I'll treat them like we did in the previous question, really as the power of half. Let's go ahead and just convert that. So it is the square root. We're just putting power of half to simplify the differentiation. So that'll give us half times 100 plus x squared to the power of negative half, and then the derivative of the interior is going to be 2x. Similarly, for the second square root, so it's plus half times x squared minus 72x plus 1,321 to the power of half. And that's got to be a negative power of half times the derivative, so 2x minus 72. Again, I want to kind of simplify that derivative. So it's going to be in my numerator 2x over 2. So I see my 2's are going to cancel there. So I'm just going to cancel them right away. Over 100 plus x squared to the power of half. And then for my second equation, I'm going to have 2x minus 72 over the half goes down there. So again, I have a cancellation. 2 divided by 2 is just 1. 72 divided by 2 is 36. Over x squared minus 72x plus 1,321 to the power of half. So there I've got my derivative function. I want to set it equal to 0 and solve. Now, solution for this question is a lot of algebra. So another strategy we could use is take this to a graphing calculator and just find where it's crossing the x-axis. So I'm going to take this over there just to simplify the solution process. So I'm going to take that function we just wrote. It's a distance function, so f of x is the derivative of the distance function. So it's x over x squared plus 100 to the power of 1/2 plus in numerator x minus 36 over x squared minus 72x plus 1321 to the power of 1/2. So that gives us this very flat function. We don't really see where it's crossing the x-axis currently, so I'm going to zoom out until I see where that is, and then I'm going to zoom back in. So it looks like it's here in the vicinity of 20 where the function's crossing the x-axis. So I'll just zoom in to find that point, and it looks like that's the point 24, 0. So that's what we're looking for. That's where the function equals 0. And that gives me enough information to go back. So I'm just keeping in mind that that was 24. So the solution here is 24. I'm just going to mark here that this is a graphical x-intercept. That's how we found that value of 24. So let's just be sure we answer the question, where should the stake be placed to use the least amount of rope? It should be placed 24 feet from the 10-foot pole. And if I look here, 36 minus 24, that's a distance of 12. So it's also going to be 12 feet from the 5-foot pole. And I'll box that. That's our final answer there. Thank you for joining for this investigation of 3 optimization examples. See you soon.